In this video, we're going to talk about how to calculate the future value of a simple ordinary annuity. An annuity is a series of payments or investments made at regular intervals. A simple annuity is an annuity in which the payments coincide with the compounding period or conversion period. So for example, if the compounding frequency is monthly, then the payments are made once a month. An ordinary annuity is an annuity in which the payments are made at the end of each interval. We're going to talk about simple ordinary annuities in this lesson. So for example, if we have a compounding frequency of monthly, then the first payment will be made 1 month after starting the annuity, and the payments will also be made monthly. So let's develop a formula. Suppose Diane opens a simple ordinary annuity, making regular payments of $100 once a year at 5.0% per annum compounded annually. We'd like to know what will the value of the annuity be in 4 years. So what we're going to do is we're going to say, if you recall, we said when you open the annuity, our assumption will be that your first payment is at the end of your first period. So since it's an annual compounding frequency, we're going to say her first payment will be 1 year from today. Her second payment will be 2 years from today, her third one 3 years from today, and then we'll close out the annuity with her fourth one being 4 years from today. Now, to be honest with you, most of the time, annuities, there's many more than 4 payments, and the compounding frequency is not so long as yearly. It's much more frequent than that in most circumstances, but this is a good one for us to establish our formula. So what we're going to say is we'd like to know the value of the annuity in 4 years. Well, the value of the annuity will be equal to the sum of the values of each of the 4 individual deposits. In other words, if we can figure out how much that deposit is worth at the end, and then how much that one is worth, how much that one is worth, and how much that one is worth, and then add them all together, we'll have the total amount. So that'll be our strategy. Well, on the day that we close this annuity and Diane makes a payment of $100, that payment is obviously worth $100. It's literally contemporaneous with the closing of the annuity. So it's worth $100 at that moment. Now, that payment that she makes 3 years from today, well, that payment will have had 1 year in which to accrue interest at 5% per annum compounded annually, so it'll be worth $105. The next one, 2 years from today, well, that'll be worth $100 times 1.05 quantity squared because it's had 2 compounding periods. And the first deposit that she makes 1 year from today will have had 4 years from now, when we're calculating this, 3 compounding periods, so it'll be worth 100 times 1.05 quantity cubed. So the total value of her annuity will be $431.01. But now let's recognize that if we had to do that, add up the values of all these annuities, of all these deposits every time, the future value, it would take a long time. So what we're going to do instead is see if we can develop a formula. Notice that we're adding the 4 terms together, and every term is equal to the previous term times 105. We have 100. And then 100 times 1.05. And then that number times 1.05. That number times 1.05. What it really means is we're looking for the sum of a geometric series. A is 100, and R is 1.05, and we're adding the terms. Well, that's kind of a good place to start. So we see that A is 100, R is 1.05, and it says here N is 5. That should say N is 4. And so the sum of the first n terms, the sum of the first 4 terms will be 1.05 to the exponent 4 minus 1 times 100, and then divided by 1.05 minus 1. All we're doing here is we're using that formula right here that we learned earlier when determining the sum of a geometric series. And that answer is $431.01. So what we see is we can use the geometric series to determine the future value of an annuity by letting A be the value of each individual deposit, letting R be 1 plus I, and then evaluating I and N the way we do in compound interest questions. So to repeat, we can use the geometric series to determine the future value of an annuity. by letting A be the value of each individual deposit, R equals 1 plus I, evaluating I and N as we do with compound interest questions. And what we can do instead is say A is equal to the regular payment, R is equal to 1 plus I, N is N, and then subtracting 1 stays the same. And since R is always equal to 1 plus I, our denominator of 1 I of R minus 1 will be 1 plus I minus 1, which will just be I. And so what we have here is a formula that many students prefer to use. Okay? So let's put that into use. Determine the future value of a simple ordinary annuity in which quarterly payments, once every 3 months of $1,000 are made for 30 years at 4.4% interest compounded quarterly, and then also determine the amount of the interest earned. So we want to know what our future value is. We know our regular payments are 1,000. N will be 30 times 4, 30 years times 4 because of quarterly payments. I will be 0.044 divided by 4, 0.044 because the annual interest rate is 4.4%, dividing by 4 because we're doing it quarterly, and we get 0.011. Plugging everything into our formula, we get a future value of $246,958.07. So if we stick to this commitment of putting $1,000 in every 3 months for 30 years at that interest rate and compounding frequency, at the end of those 30 years, we'll have $246,000 and more than that. So that's the future value of the annuity. Now, to determine the total interest earned, what we're going to do is we're going to say, well, there was $1,000 per payment, and she made 120 payments. So what she actually put into the annuity was $120,000, but the future value is 246 and change $1,000. So we're simply going to subtract. This is, if you like formulas, hopefully this makes sense to you. The total interest earned is the future value minus the total payments made, which in this case is $126,958.07. Notice that that's more than the actual money that went in. So if you're clever, you can get this compounding interest in your life to work in your favor. Now, how much will New Swan need to invest every 6 months at 5% per annum, compounded semi-annually, to be a millionaire in 40 years? And then how much of that future value will be interest earned? So New Swan is a young man who wants to become a millionaire in 40 years. So what New Swan needs to do is use this formula. He knows his future value is $1 million, so he plugs that in. R is what he's looking for, but he wants to know what the regular payment needs to be. His I value will be 0.025, calculated the usual way. His N value will be 80, calculated the usual way, and that's right there. So what he can then say is that 1 million divided by this value will equal R. So instead of dividing by this value, what we're doing in this step right here is we're multiplying by the reciprocal, which is what dividing a fraction really is. So we're saying 1 million times the reciprocal of this circled thing will be his required regular payment. That equals $4,026.05. So what we're saying is the semi-annual payments will need to be $4,026.05 for New Swan to be a millionaire. So if New Swan can come up with $4,000 twice a year for the next 40 years, he'll be a millionaire. That's good to know. Now let's figure out what the interest earned will be. Well, the total payments he will have made will be $4,026.05 times 80 payments. So he will have made a total of $322,084 in payments. The interest earned will be the future value minus the total payments made. So $1 million minus $322,084 is $677,916. So that means that the total amount of the interest when he's a millionaire will be $677,000 and change. And that's more than 2/3 of the future value. So in other words, more than 2/3 of it will be interest. And so again, that's why it's really good to get interest working for you in your life rather than against you. Now imagine Yvette opens a simple ordinary annuity in which she's going to pay $402.31 per month at 4.2% per annum compounded monthly. She wants to know how long it'll take her to have a value of $500,000. So in this case, what we do is we say, okay, our future value is 500,000. Our regular payments are $402.31. Our I value will be 0.042 divided by 12, and N is unknown. So we plug everything into our trusty formula. 500,000 equals 402.31 times the fraction 1.0035 to the N minus 1 all over 0.0035. So we divide both sides by 402.31, and then we multiply both sides by 0.035, and then we add 1 to both sides. And then what we have is the value of 1.0035 to the exponent n. What we now have to do is use logarithms. N will be equal to the log base 1.0035 of this value right here. And as you know, we can do this a couple of different ways, depending on what kind of calculator you have. But what you end up with is an n value of approximately 480. Now, that doesn't mean that n that it takes 480 years. Recall that in a monthly question, n is the number of years times 12, which means the number of years will be n divided by 12. 480 divided by 12 is 40. So we can say it'll take roughly 40 years for her future value to be $500,000 by making, for some people, that's a doable commitment, making those payments each month for 40 years. Okay.